75.3 kilojoules per kilogram. And H hat at 300 degrees C, 1 bar, is 3074.3 kilojoules per kilo. So plugging them in this equation, the result is going to be that the final mass enthalpy is going to be 1/2 of this plus 1/2 of this, and the result is 2974.8 kilojoules per kilo. Steam tables don't have, of course, continuity of values. It's reasonable to assume that the answer is going to be close to the midpoint, since it's half and half, so close to 250. If we look at steam tables, at H hat at 250 degrees C, 1 bar is 2974.3 kilojoules per kilo. So it's close, but not exact. So what can you do if you want to get a more exact answer than 250? Interpolate. Exactly. So if you interpolate, the difference, it's between, this value is between this and the value at 300. So we interpolate between 250 and 300. And the difference between the two, between this and this is 0.5. So the temperature is 250 plus the difference in temperature is what? 50 here, right? And the difference in enthalpies is 0.25. What's the difference in enthalpies between 300 and 250? It's 100. It's exactly 100. 199, sorry, 109. Wait, I'm looking. Yeah, it's exactly 100. Yeah, 297. Okay, this is the difference between 2974.8 minus 2. Okay, let me write it here. Interpolating. Temperature is going to be 250, the lower bound, plus the distance between the temperature between 300 and 250 is 50, times the difference between the enthalpy I have, which is 297, minus the enthalpy of the lower bound, over the upper bound, which is 3074.3 minus the lower bound. Okay, so that's your standard interpolation formula. So that's 250 plus 50 times 0.5 over 100. And that gives us 250.25 degrees. So pretty close to the midpoint, a little bit high. Yes, ma'am.
we were able to make a correlation that was very, very close, would we be able to just say close enough check mark, or would you like us to interpolate?
I would probably want it to interpolate. Where would it be exactly the midpoint?
Ideal guy.
Ideal. Stem is not ideal. So that's why you said. Okay, clear everyone? So that's the temperature of the mixed stream. Now what is the enthalpy? The entropy generated. We'll do the entropy balance. So the entropy balance is final mass times final enthalpy minus beginning stream 1, unmixed 1, unmixed 2, so that's the total beginning entropy, equals we had no streams in or out. We have a diabaric process, so there is no Q over T. So is the process isentropic? Better not be. It's a mixing process. So plus S generated. So that's the generated entropy that we need. So it's going to be 2 times final minus 1 times 200 minus 1 times 300. Steam tables give us also mass entropies. So from steam tables, we will find S hat at 200, 1 bar, that is 7.8343 kilojoules per kilojoules per kilogram Kelvin or C. So that's S hat 1, S hat 2, which is at 300. Is 8.2158, same units. And S hat final is at 250, actually let's write it 250. 250 S hat at 250, 1 bar is 8.0333. And how do I get a 250 and 25? Okay. So I want S hat final, which is at 250.25, 1 bar. And you see why I answered no, it's not good enough to say you don't need to interpolate. Because when you come to entropies, as we'll say, there will be a significant difference if you interpolate it or not. The answer I will come up now is different from the answer that you text us by about 20%. So that's going to be the minimum value plus the distance in temperature from the interpolation point from the minimum is 0.25. And I have total distance 50, so 0.25 over 50 is how far I'm going to travel. And the distance between the 300 and the 250 is 8.2158 minus 0.033. And that gives us 8.0342. So, as generation, and you multiply by kilogram the generation, okay? You multiply this by the masses. So generation is going to be kilojoules per Kelvin. Okay? So S generation is going to be 2 times 8.0342 minus 1 kilogram times 7.8343 minus 1 kilogram times 2, 8.2158. And the result of this calculation is 0.0183 kilojoules per Kelvin. What answer does the text have for the generation?
0.0165.
Exactly. Text has 0.0165. That's because text did not interpolate. If you don't interpolate, you get, okay, so I guess more like 10% off. But still, significant difference. You would think, what's the difference here in temperature? 250 versus 250.25. And that's in C. If you add in Kelvin, it's even less percentage, right? Plus add 273 for Kelvin. So we're talking about 0.3 over 500. So that's 0.6 over 1,000. So that's 0.06%. So 0.06% distance in temperature resulted in a 10% difference in temperature generation calculation. Okay. Why did I do the interpolation there?
To show it.
No. I did it because I did the same problem in unison. And I got the 0.0183. And then I had to figure out why is it 10% different from what the text has. And the difference was the interpolation. Okay. All right. Everybody clear on this? It's all review, right? Entropy balance clear, one? All right. So, let's do the very same problem. Let's do the very same problem now in unison. Now, unison has 2 incorporated steam tables. Those packages can be used only if water is your only component. If water is something else, you have to go to one of the standard thermodynamic packages. But if you have only water, so let's start a new simulation. Oh, I'll see if I turn it on. Sorry for that. And let's lower this thing. Oh. Okay, I didn't tell my computer this. So we start a new case study. You can save the previous one if you want. Up to you.
It goes back to it.
I'll save it. Nothing else for my correction. All right. So we'll start a new case study. In this case, what components do we have? Only water. Even though I had water in the previous example, I had something else. It wouldn't have allowed me to use the incorporated steam table. So put water. Okay. Everybody has other water? I'll give you a couple seconds. All right. X here, fluid packages. Click Add. There are two steam tables. One is ASME, I guess that's the Mechanical Engineering Institute. And the other is NBS, National Bureau of Standards. There's not much difference between the two of them. Both of them mirror what steam tables give you quite well. I prefer to use the NBS, I'll use the NBS, but you will not get much different using the other. So we want to select NBS steam. If I had the second component on water, it wouldn't have allowed me. So click that, enter simulation. Now, unison everything is continuous processes. It's not beginning and final state. Can we think of the analogous problem in continuous processes?
Well, what I said?
About what Juan said. You have two streams continually flowing, and now it's flow rates. So here I had mixed 1 kilogram and 1 kilogram. Let's say I have 1 kilogram per hour at 200 and 1 kilogram per hour at 300 mixed adiabatically, and what comes out. That's what we're going to simplify. Okay? Yeah. So we're going to create two streams. One thing, for this we will need more significant figures, so before we start, let's change our significant figures to 5 to 6. Let's change them to 6. So let's go back to Tools, go to Preferences, go to Variables. Tools, Preferences, Variables. One is more time.
I need more time. Hold on.
Okay, let me do it again. So you go to Tools, go to Preferences at the bottom, and then select the tag Variables. Not simulation here, Variables. And then select Formats. And if you click the Format tag, you select all of them, and select Format, Significant Figures, type 6. All right? Okay. So the analogous
We
continuous
need to
program.
click save preferences. You just click X,
No, you-
but like on the bottom, since yours was already 6 sig fixed, do we need to click save preferences or just X?
Yeah, just X.
I think X works fine on this. You don't have to say it's not an okay key.
Okay. So just ask.
No, it's a good question, and I hope I answered it correctly.
No, I think I went back and checked. You click X over.
Click the actual tab, he says one.
Yeah, sorry. Should I do it again? Carmen, okay? When is up? Everybody okay? All right, so let's create the two streams. So the streams coming in, I guess one is a good name for it. Even though there's only water, the only component still has to define the composition. Okay, I want to fast. Click on the material stream, drag it over and release, and you get material stream 1. All right? Okay, double click on the, I guess I'll put here, stream. Double click on the stream, go to composition. Put mole fraction 1. Pops up, click OK. So go to composition, type 1, click OK. And now go to conditions. And for this stream, do you have SI unit?